In the Water Research Center at the Tel Aviv University. I'm the Vice Director, and I'd like to talk about water technologies. So we all know about the importance of water. We know that life on Earth is impossible without water, and that about 70% of our body consists of water. But the sad news is that by 2025, more than one-third of the population in the world would live in areas with inadequate water supply. And if we look at some statistics from the WHO, we can see that about 1/6 of the people in the world would not have safe drinking water. About 1/3 will not have access to sanitary systems. And we have more than 5 million people die every year in the world due to water-related illnesses. And out of them, 2 million are from diarrhea-related illnesses. So when we look at global trends, we know there is population growth. We know there are issues with uneven distribution of our water sources. And we also know that there is an extreme use of chemicals in the world, synthetic chemicals that we generate and manufacture, and these contaminate our water sources. And the list of chemicals is endless, and I saw that you even have water analysis here. So the list is endless, and I will talk today only about a specific list of chemicals. And but we know there are also issues with radioactive substances. We have issues of inorganic chemicals due to the use of nutrients. We have issues of sewage contaminating our water. We have also thermal pollution from power plants, also disease-related agents, and organic compounds. Basically, in order to apply a sustainable way of thinking, even as engineers, and I assume most of you are engineers, all of you, none of you? You're not engineers? Okay. So my talk will be very engineering-oriented, but anyway, in order to think of water in a sustainable manner, we need to use all our water resources, not for only our generation, but we need to think about the future generation. And we need to conserve water. And I think Israel is an expert in water conservation and technologies to help in water conservation. But we also need to reuse our water. And actually, water reuse is one of the possible ways to sustainably use our water sources. And basically, water reuse is taking wastewater, purifying it so it can be used for other purposes than drinking water. So also in Israel, we don't reuse water for drinking. Although there are some countries in the world, if you look at California or Singapore, they have direct potable reuse, which means they treat their wastewater and they directly augment, for instance, surface water. 10% of the surface water is augmented with treated wastewater, and this goes directly to drinking. In Israel, however, it is not possible to do this, also due to religion issues. So we do not use the wastewater directly for drinking. But we do treat the wastewater, highly treated, and use it for irrigation. So that way it doesn't go directly to drinking water consumption. But water reuse is, for example, in Israel, which is a semi-arid country, is one of the ways to augment our water supplies and to reduce potable water. So the need is the increasing need for water reuse, which is actually treated wastewater. The source is municipal wastewater as a major source. In Israel, and almost 99.9% of the wastewater goes to a municipal wastewater treatment plant. And so this actually allows to treat the wastewater and use it as a water source. However, there are risks. And one of the risks of using this reused wastewater is emerging contaminants in the wastewater. So for example, the traditional wastewater system is not used to reduce the pharmaceuticals, the pesticides, and the personal care products. And therefore, there's an increasing need in advanced wastewater treatment for treating those contaminants. And if we look here through this image, we see here we have the raw water. After drinking the water and using it, we have the wastewater, which reaches ideally to the wastewater collection system. Then it's treated through secondary treatment, and it can be reused after secondary treatment, which is a biological mechanical based treatment. However, we can also utilize tertiary treatment, which can be related to filtration and disinfection of the effluent, and we can also reuse wastewater here. But also, we may utilize advanced treatments, which is one of the which is my research expertise. We can utilize advanced treatments to reuse the water that is free of pharmaceuticals and personal care products and pesticides. And as I previously said, urban wastewater treatment is not designed to break down the drugs, pesticides, and personal care products. And therefore, if we reclaim this water and use it for irrigation, we introduce into our soil all those chemicals. And then, of course, there's an uptake of those chemicals in our food supply, and also this water can penetrate to the groundwater sources. So basically, if we reuse wastewater, ideally we need to treat it in the perfect way. And this is just an illustration. If you can see, this person takes the antibiotics, and most of the antibiotics that we consume or drugs that we consume reach the wastewater treatment system, because our body can only metabolize a really small portion of the drugs that we take. So most of it goes through our urine. And so it's not much of a difference to utilize the drugs or to dump it directly to the sewer. It's pretty much the same. And if we look at the world, okay, because in some places in the world, these contaminants are regulated. And actually, there's only one country in the world that currently regulates those chemicals, because it's very expensive to treat them. And this is Switzerland. So basically, what Switzerland did is that it regulated the pharmaceuticals. And 100 out of 700 wastewater treatment plants must be equipped with ozone or powdered activated carbon absorption in the next 20 years. So, and this is in order to treat those pesticides and pharmaceuticals. Also, they regulate the polluter pay principle. And this, if we have big pharmaceutical companies that are very rich, right? They have a lot of money, but but their wastewater is heavily loaded with the drugs. And this wastewater directly goes to the environment. So this is, of course, not fair. And they implemented the polluter pays principle, which if you pollute, you need to pay, especially if you're a rich company. And this is actually happening in all the world. The pharmaceutical companies, they have this money, but they don't pay the cost of contaminating the environment with all those drugs. And also, Switzerland, they set a list of indicator compounds. It's not possible to regulate million synthetic organic compounds that are manufactured. Okay, just think of the amount of organic compounds that are manufactured every day. We cannot regulate all of them. It's impossible. So similarly to disinfection, where we measure the coliforms and the E. coli or the fecal coliforms, also with the micropollutants. So they decided, okay, let's have a list of pollutants that we will regulate. And if we have 80% reduction of these pollutants in our wastewater treatment plant, then we're okay. So basically, the compounds that they regulated are sulfamethoxazole, which is an antibiotic, diclofenac, which is a painkiller, herbicides, corrosion inhibitors, and anti-epileptic drugs. Okay, which basically, when we consume them, most of them reach our urine, and from there it goes to the wastewater treatment plant. And they did something innovative because they did not regulate for each pharmaceutical. They regulated for the treatment, for the engineering treatment. They said, okay, use either ozone or activated carbon and remove 80% of those chemicals, and you're okay. And my research is actually on generating hydroxyl-free radicals and other reactive species in the water. We all know that in our body, when we breathe, the breathing itself forms free radicals. And we know that we need to, in our body, when we smoke, when we are exposed to radiation, air pollution, okay? All these things form in our body free radicals. And then we have the antioxidants, right? Like if we eat blueberries or something like that, that that react with the free radicals, different chemicals that react with the free radicals, and then they don't pose a threat for disease or something in our body. So basically, my research is on utilizing those free radicals and reactive species and nanoparticles and all these type of nano things in the water in order to treat the water. And the only reason we're doing this is because the standard wastewater treatment plants cannot remove those chemicals. So the only way to stop the cycle of introducing those chemicals in our body is to break them down. I just want to tell you that, for example, pesticides can harm our body. And it was shown that children that are near places which they are exposed to pesticides, they have impairment in their the way they write, and they can have mental issues. So basically, exposure to a mix of chemicals was proven to be really problematic. And I know there's an issue of water, and when you don't have water to drink, you can't think about those pollutants, because you really need to think about having the water to drink. But anyway, I'd like to present you these possibilities for advanced treatment that are utilized in some places in the world, and also in Israel we have pilot plants, and we're trying to implement those those treatments. Okay, so those free radicals are extremely reactive, and as you can see here, they can break down pesticides, herbicides, bacteria, viruses, and whatever to treat our water sources. And you can see here that the hydroxyl radical has one of the highest oxidation potential. So basically, it's a really strong oxidant, much more stronger than chlorine dioxide, hypochlorous acid, chlorine, ozone, or hydrogen peroxide. So in general, to summarize, the hydroxyl radical is really reactive, short-lived, unselective. However, when we generate those radicals in the water, we really have a low steady-state concentration. And in wastewater, we produce those radicals by ozonating wastewater. And this is because ozonation of wastewater can go through the direct reaction in which the ozone itself oxidizes the pollutants, or through the indirect reaction where ozone reacts with natural organic matter in our water to form the hydroxyl radicals. So basically, we all know that in treated wastewater, we have a lot of organic matter. And the ozone reacts with the natural organic matter and forms those hydroxyl radicals. And we have many parameters that are affecting ozonation, like the dissolved organic matter in nitrite. I saw that you measured there, I think that was nitrate. And there are advantages to the use of ozone because we can remove the trace organic carbon. We can add oxygen to the effluent and also increase the biodegradability of our wastewater. And ozone is widely used for drinking water, but now in the world we're trying to recently implementing ozone for reclaimed wastewater, and it's known as BAT. BAT is the best available technology today for treating those contaminants. However, because ozone increases the biodegradability of the wastewater, if we don't want to form biofilms in our waters, in our pipes, we need to use biofiltration. So the golden rule is ozone and biofiltration for treating reclaimed wastewater. And you can see here different configurations in various places in the world. Most of them are in the USA and Europe, okay, which they use ozone, and after that, a biological treatment that polishes what the ozone did. So the ozone breaks down the organic contaminants to smaller units, and the ozone can polish it. So because I want to show you several of my projects, and I don't know how the time is, I will scan really quickly with the technology and more discuss the application and the implementation, okay? Okay. So basically, I'd like to tell about Israel. Israel is a leader in wastewater reclamation and reuse. We utilize more than 85% of our wastewater for irrigation after treatment. So basically, in Israel, wastewater is a water source. We're in a semi-arid country. We do not have water. And reclamation and utilization of this wastewater and treating it in a very high level allows us to use it as a water source, especially for the farmers, since they cannot pay the money for the potable water. I'd like to discuss, actually I have here 4 projects, but I really do have 2 more, so let's quickly scan those projects. And the main common thing with all these projects that they all utilize those free radicals that I discussed before. And I want to show you what we can do with advanced treatment possibilities. Okay, so this is one of the largest wastewater treatment plants in Israel, and it has a secondary treatment with activated sludge and tertiary treatment, which is soil aquifer treatment. Basically, what we do is, you can see here, the water after secondary treatment is recharged into a basin, infiltrates into the sandy soil, okay? And after a hydraulic residence time of about half a year, we pump this water, and this water actually irrigates all southern of Israel. So, and the quality of this water is very high. After secondary and tertiary treatment, which is percolation through the soil, the treatment is very high. However, we have some issues with this water. First, the effluent, which percolates through the soil, has a very low oxygen content. So this results in manganese and iron dissolution in the water. So what do we care about manganese and iron dissolution? When the farmers take this water through the drip irrigation systems, the manganese and the iron seize oxygen again. They form colloids or manganese dioxide, which clogs the drip irrigation systems. So this is a major issue. And therefore, we have clogging of the drip irrigation systems. We have also trace organic compounds in the water because we use treated wastewater. And also, we have a very hydraulic load. Because Israel is a really tiny country, we don't have much land, and therefore, we have an issue of population growth and increase in wastewater, but we don't have more land to percolate the wastewater through. So if we can improve the treatment by technology, and I just want to show you here, if we can reduce the residence time from half a year, let's say to 1 month, we can have on the same land more treated tertiary wastewater. So this was our goal in the project that that was granted through a German-Israeli grant, and I was the leading researcher from Israel. And basically, pharmaceuticals is a problem occurring throughout the world. It's not related to Israel. My colleague, Professor Avisar, also we worked together on this project, but he was not able to get today here. And we found a list of pharmaceuticals in our wastewater. And basically what we did, we took the secondary effluent through biofiltration, ozonation, and then short soil aquifer treatment. So basically, by pre-treating the secondary effluent with these treatments, we were able to shorten the aquifer treatment to 1 month and receive the same quality of water. And we did this by biofiltration. It's just a simple granular filtration. We added coagulation and flocculation, but we also added another thing, which is hydrogen peroxide. The hydrogen peroxide actually allows us to provide available oxygen to the biofilms in the biofilter. And this way we were able also to remove ammonia, because one of the problems with the wastewater in Israel that we have it's very hot in Israel, and we have a very high ammonia concentration in the wastewater. Then we ozonated the wastewater, and we percolated the ozonated wastewater, which we had a very high oxygen content, into the soil. And just to make the story short, and we were able to remove the DOC, we were able to remove the UV absorbance of the water, and we were able to remove the manganese concentration in the treated wastewater to a level that does not clog the drip irrigation systems. And also we were able to remove the micropollutants. OW is the observation well, is the last treatment. However, when we oxidize water to remove micropollutants, we need to be careful that we don't form another monster, because we do not oxidize the organic compounds to CO2 in water. And so what we did, we also studied the byproducts. And if we look at this compound, venlafaxine, I don't know if you know about this, but this is an antidepressant. It's one of the most prescribed antidepressant in the world. And actually it's called Effexor or Trivilo, okay? And it's the 6th most commonly prescribed in the US retail market. And our wastewater is heavily loaded with this antidepressant. So when we irrigate treated wastewater that does not remove those chemicals, we just consume them in some other way. And therefore, what we saw is that when this is the chemical molecule of venlafaxine. So when we ozonate it, we receive a byproduct. And the byproduct, when we remove the mother product, the byproduct concentration increases. So what we found is that we need to increase the ozone concentration also to remove the byproducts. So when we study the breakdown of chemicals, we need to also study the byproducts of the process. Because, you know, in environmental research and technology, nothing is perfect. Every time you do something, you have residuals. And if you don't manage and treat the residuals, then you didn't look at the whole picture. And as environmental researchers, I think we need to widen our, the way we think and look at things. Okay. So what we have achieved removal of the organic compound, improved the removal of the trace organic compounds, and efficiently prevented manganese dissolution. Okay, so how much time do I have left? I want to show you a few more projects.
You can take another 10 minutes.
Okay, so I'm known to talk really quickly. So I have 5 projects in 10 minutes, which is 2 minutes per project, right? Yes, okay. So I'd like to talk about another pilot that we have. Hospitals. Hospitals have wastewater, and their wastewater is not regulated in anywhere in the world. Actually, the wastewater from the hospital directly flows to the domestic wastewater treatment plants. And of course there's a problems, because we know in wastewater, in hospital, people get really difficult chemicals. And for example, in one of the hospitals in Israel, we built a pilot plant, in the oncology department. Actually, it's called the cancer center. So people that have cancer, they get to the center, get treatment, and when they urinate in the center, most of the chemicals that they get to the wastewater. And so basically, we have a leading pilot plant that is aimed to remove those contaminants. And what we're doing is that today we're mostly thinking about treatment in the source. Okay? So if these contaminants reach the domestic wastewater treatment plant, it's too difficult to treat a huge volume of wastewater. So if we treat specific sources, it's much more simple. But we're not interested in the cooking and drinking water. We're not interested in the personal washing water. We're only interested in the wastewater that comes from the cancer center. And we're also interested in other centers like the radiology, that you get all the iodinated contrast media chemicals. So basically, we took only the wastewater that we're interested in and treated through a membrane bioreactor followed by ozonation. And this is the images of our pilot, okay? So, and it's in the hospital in Israel. And actually, it took us 2 years to have permission from the hospital to put this pilot in the hospital. They didn't want, our university really got tough on this. They said, okay, let's have it work. So even as a scientist, we tried to implement this project for 7 years. But no hospital agreed. They all said, no. We don't want research. We don't want that our wastewater quality will be exposed. But this hospital stood up for this issue, and bravely they agreed that we will implement our treatment there. And also, one of the issues that we were not, we stood up was to not to hide the results. So what we'll see, we'll talk about it, definitely. And this issue is a worldwide issue. And the only way to stop chemotherapy drugs and other iodinated contrast media or other drugs reaching the environment is by treating it in the source. So this is our goal. I'll very talk about solar disinfection. We're also doing work on solar disinfection because in Israel we have a lot of sun. But the sun itself is not strong enough to break down the chemicals and disinfect viruses in the water. So therefore, this is a project, a big European Union project that we work together, which we actually coat ceramic membranes with a photocatalyst in order, again, to form those hydroxyl radicals that can break down the micropollutants and inactivate the microorganisms. And this surface can also be an anti-biofouling surface. So I don't have time to discuss results, but I'll go to the next project. And this is a pilot system which we implemented to that the ceramic membranes were coated with a doped titanium dioxide coating, and which utilizes also the visible portion of the sun. And this is very important to utilize also the visible portion of the sun in order to treat the wastewater. This system was situated in Jordan, and we had one in Africa also as well. And this is the pilot system. This was in Jordan. And really quickly, I would like to talk about also utilizing those free radicals in order to form bioethanol. As we all know today, there's an issue of food versus fuel. So countries utilize corn and starch and sugar cane and beet in order to form bioethanol, which is actually ethanol. And the issue is that we have an equation that we want to break. We don't want to use food to make fuel. We want to use waste to make fuel. And our research was granted by two grants, is actually on using agriculture waste, which we anyway have, in order to form fuels. And so we're now in almost the third year of the project. And just to make things short, we're ozonating the agriculture waste or paper mill waste or municipal trim waste or olive oil mill waste. And this is because in Israel we're a Mediterranean country and we have a lot of waste from olive oils in order to form the bioethanol. We have a lot of obstacles to go through. But this is also another research that we're doing. And just really quickly, we're also working on biosensors, which are microbes that illuminate light upon a reaction to some signal. And we're working on biosensor development in water disinfection. Because in water disinfection, we do not have biosensors that can actually measure advanced oxidation processes. And I'll just want to say that we're also working on biofouling control, which is basically using advanced oxidation to treat biofilms. Biofilms is in the water pipes or on the reverse osmosis membranes. Whenever water flows through a system, we have a biofilm form. For instance, if you take a glass of water and put it in the sun and come in a week, you'll see some sticky slime forming. This is biofilms. So biofilms is a major operational problem. And in this research, it was a 5-year research granted by the Israel ministry, which we implemented technologies to remove the biofilm. And this is just a cute image to show the red are the microbes and the green are the EPS, which are the extracellular polymeric substances, which the microbes excrete in order to form the biofilms. And I'll just like to talk about just a few seconds about our Water Research Center. The managing director is Professor Avisal. I'm the deputy director, and these are the different units that we're working and doing research on. And I'll also like to tell just a few things that in Israel we have summer programs and also bachelor and master and PhD programs for studying in Israel. And also some of the studies are fully granted with the tuition and also some stipend for living and also medical health care. And we have students from India coming to Israel. I think mostly they like in electrical engineering, I think, but basically also there's a summer program in food security and also in environmental studies, which are related more to policy and economics. So thank you very much. It was a pleasure.